All right, guys, so continuing our trig unit here, we kind of talked about writing angles in standard position and then coterminal angles and things like that. So I want to do a little brief review on some of that stuff and then get into one new concept, which is all about reference angles. And that'll lead us into a larger topic called the unit circle, which we'll get into in the next section. So let's get back into it. This was from the Springboard book, and there's just a few examples. If you happen to have your book, you can kind of follow through. But again, the idea is when you're writing an angle, okay, because we want to eventually be able to have angles larger than 180 degrees. So we're not going to just be stuck inside right triangles all the time, or triangles in general. We're going to open it up to like complete circles, and then as we saw before, you can even have bigger than 360 degrees and have a more than one rotation. So really it goes on forever. But the key here is when you are drawing angles in standard position, you always start out with the initial side being the positive x-axis, and then the terminal side will just end wherever it needs to end. And positive angles end up going counterclockwise this way. So if you take a look, there's a couple examples in here, 120 degree angle. Again, if you had to draw that in standard position, you're always going to start out on the x-axis in the positive direction. We know 120 is a little bit past 90, so it's going to end up in the second quadrant there. And that would be our 120 degree angle. Okay, to handle negative angles, again, they always start with the positive x-axis. Now this one, since it's negative 200, you would just go 200 degrees clockwise. So you're going to go down through quadrant 4, then quadrant 3, and you have to go a little bit past. Sorry, I missed the spot there. But again, the other part of the x-axis would be 180, so we needed to go about 20 degrees past that. So we actually went negative 180 and then 20 more to end up where we did. Okay, so let's place an angle on the coordinate plane here and find the sine, cosine, and tangent of the angle formed, just as a little review. So if the terminal side in standard position goes through the point 3, 4, okay, so 3, 4 over here. Okay, I know again they always start at the origin. This is the initial side is right here. The terminal side of the angle is going through that point they told us, right? So that's the point 3, 4. Find the sine, cosine, and tangent of the angle. Right, here's the angle. There's an angle formed there. So the trick is to draw yourself a little right triangle. Okay, so we're going to think about a right triangle being here, here, and here. Okay, we're going to get a right angle right there because we drew, on purpose, we drew that segment straight down to the x-axis and then use the x-axis as the other side of the triangle. So we do have a right angle formed. And we should be able to find the sine, cosine, and tangent of the angle. Okay, if we think about going back to previous sections even, sine being opposite over hypotenuse, cosine is the adjacent over hypotenuse, and tangent is opposite over adjacent. Okay, from the location, our angle is actually right here, so the adjacent side, and the way we're going to set things up, when I was talking about reference angles in a little bit, the adjacent side will always be the x-axis. Okay, the opposite side will always be like the y direction, and then the actual, from the origin to the point, that will always form the hypotenuse of a right triangle. Okay, so we should be able to figure out the lengths of those sides, and then we can write the three ratios that we need. So for example, what I mean by that, if we look, the adjacent side length is just going from 0 to 3, right? So the adjacent length is 3. The opposite length is 4. Okay, so again, those are just the x and y coordinates. Those are going to be the adjacent and the opposite. And then the hypotenuse, how do we find the hypotenuse in a right triangle? Well, if you know the two other legs, Pythagorean's theorem, right? 3 squared plus 4 squared is going to equal the hypotenuse squared. So just to save a little writing space here, 9 plus 16, so 25 is the hypotenuse squared. So that makes, when we take the square root, the hypotenuse would end up being 5. Okay, and this is a classic 3, 4, 5 right triangle. Okay, that's one of those Pythagorean triples, if you're familiar with those, just different patterns that show up based on side lengths. But now that we know the side lengths, we can go back to SOHCAHTOA stuff, right? So the sine of that angle, remember the angle formed is right here. We don't know the measurement. We could find it on a calculator, but we don't need it. This one just says, what is the sine of the angle? So the sine of any angle is the opposite side over the hypotenuse. So in this triangle, the opposite is 4, and the hypotenuse is 5. Okay, cosine is always adjacent over hypotenuse, and then tangent is always opposite over the adjacent. Okay, so we could do that for any, they could give you any ordered pair. On the terminal side, we could draw ourselves a little triangle there. It could end up in any of the quadrants. Maybe the x coordinate was negative. We ended up in the quadrant 2 over here or something. So keep that in mind once we get into this next little idea of reference angles in a bit here. That's kind of what this was a little preview of. Okay, and a good reminder of the SOHCAHTOA stuff. Okay, so this was just a couple more examples of drawing angles in standard position. The ones that may give you a little more difficulty just because we're not as familiar with them, like something like C, if they give you something in radians, at this point it might just be in your best interest to convert to degrees. So just as a review on that, if we remember 180 degrees equals pi radians. Okay, now eventually we'll, once we're more experienced, we won't have to necessarily convert. We'll know where these are. But if you had to draw 5 pi over 6, again, at this point, most of you are probably like, I have no clue where that is. You can always do the conversion factor where what we did was we multiplied by, to get it into degrees, we would multiply by 180 over pi. Okay, and the idea is that these pi's cancel out. So we end up with 5 times 180 divided by 6, okay, and if we see what that ends up equaling, let's see, if we just calculate that out, 150 degrees, okay, and now it's a lot easier to visualize 150 degree angle, right? I know that 90 degrees is the y-axis up there, 180 is over here, so we are like 30 degrees short of the 180, so that angle right there, that's going to be your 5 pi over 6. It's equivalent again to 150 degrees. Okay, and again, a lot more practice coming on that, converting back and forth, and just kind of knowing what they are without having to do all the calculations. And the other kind of review topic was this idea of coterminal angle. And if you recall there, what we did was a coterminal would be where you would add a full circle. So like, for example, on the previous one, let's say we did a complete circle first, and then we did that amount again. And ended up in the same spot, right? Coterminal, you terminate in the same spot. What you could do to find that, if you wanted to find a coterminal angle to 5 pi over 6, you're going to add a full circle, which in radians, a full circle is 2 pi's. Okay, 360 degrees is 2 pi. So the trick is, a lot of times you need to get yourself a little common denominator. So you're going to rewrite 2 pi as something over 6, right? And 2 pi would have to be 12 pi's over 6. Right, because 12 over 6 is equivalent to 2. And that would allow you then to add the numerators now. Okay, so 17 pi over 6 would be a coterminal angle. It would end up in the exact same spot. It would, in all intents and purposes, have the same sine, cosine, tangent, all that stuff when we get there that the 5 pi over 6 did. All right, so there's a couple more examples. Coterminal, again, as a review, so feel free to look through those. With degrees, you can just add and subtract 360. With radians, again, just add and subtract the 2 pi. Okay, one other thing, as a recap, we talked about what actually a radian is. Okay, visually, what does it mean? Again, it's another unit to measure angles, okay, just like degrees. Okay, and the idea is when you extend an angle, okay, in standard position, so going this way, when I get to the point where this arc length, the yellow arc length, equals the radius of the circle, okay, when they are the same length, you get an angle formed there, and the angle there would equal 1 radian, okay, 1 radian. It's around 57 degrees, okay, it is obviously much larger than 1 degree, but it is, by definition, it is that angle formed when the arc length equals the radius. Okay, and that was covered in the previous video as well. Okay, so let's talk about this idea of a reference angle. Okay, I'm going to do a few examples here. Um, so up top here, if an angle, if theta is an angle in standard position, okay, its reference angle, alpha, is the acute angle formed by the terminal side of the angle and the x-axis. Okay, that's key. You always get back to the x-axis. So for example, if this was the terminal side of the angle, the acute angle to get back to the x-axis would be right there. Okay, so in quadrant 1, the reference angle is just the actual angle. Okay, and we'll see examples in a second. Okay, in quadrant 2 now, okay, you can see the actual angle terminates in quadrant 2. Now the reference angle is actually this guy over here. Okay, it's the one getting you back to the x-axis as fast as possible. Okay, and we'll do an example in just a second. I just want you to visualize these real quick. Okay, if you had an angle that terminated in quadrant 3, its reference angle to get back to the x-axis is going to go back up to the 180 like that. Okay, and if you're in quadrant 4, angle terminates somewhere down there. The actual big angle, you see theta, but the reference angle which we will use is actually this little acute angle. Okay, so let me do a couple examples with some numbers, and then we'll talk about what this does for us. Okay, so one other real quick little visual. We're going to make reference triangles in a lot of these, and you can see, I kind of like this way to remember it. It always kind of looks like a bow tie. It's going to be either in the first quadrant, you're going to look like this triangle. In the second quadrant, it's going to look like this triangle. But the key is, notice, in each one of these triangles, the adjacent side is the x-axis. Okay, and let's put some numbers in. I know you guys are like, what in the world's going on? Let's do a couple with some numbers, okay? All right, so for example, let's do one in each quadrant. Let's say we have ourselves an angle, and let's give it an actual value. Let's say that angle is, I don't know, 60 degrees, just for fun, okay? So that's a quadrant 1 angle, right? Okay, in quadrant 1, you don't need to use a reference angle because the angle itself is its own reference angle. Okay, so I'm going to say the reference angle, I'm going to use the symbol theta with a little apostrophe. It's actually prime. It actually equals the angle itself. Okay, we could make a right triangle out of that. That's like the one we did in the warm-up. Remember, the point was like 3, 4, and we just drew the triangle using that point itself, and we were good to go. Okay, so let's do other ones where we actually have to do some work, and then we'll see what the difference is. Okay, let's say, for example, let's say we had an angle in quadrant 2. Let's just say that actual angle, I don't know, is 150 degrees. Okay, let's just say for fun. Okay, so in quadrant 2, we need to have the terminal side right there, and we need to get back to the x-axis. Okay, so this angle right here would be theta prime. Okay, that angle, how big is that angle? Okay, if we think about it again, all the way to the x-axis is 180 degrees. Our actual angle went 150. So in this quadrant, theta prime there would be 30 degrees. Okay, because we are 30 degrees short of 180. So the rule is that in quadrant 2, the reference angle is always 180 minus the actual angle. Okay, and what that's going to let us do, that's going to allow us to draw a right triangle. Our right triangle would be here. Okay, and again, I know this is kind of weird, seeing it for the first time, so just bear with me. But what it would let you do is use a triangle, a right triangle, and we would use that red triangle there. Let's say we wanted the sine of 150 degrees. Right? You can't draw a right triangle with a 150 degree angle in it. Okay, so we would use this red triangle that had a 30 degree angle in it, and we would use it in reference to the 150. And the sine of the 30 would equal the same as the sine of the 150. Okay, same thing with cosine and tangent and all that stuff. And we'll do some examples in just a minute. Let me just get your rules for the other quadrants. Okay, when you are in quadrant 3, okay, the actual angle here, standard position, right? We start on the x-axis and go counterclockwise. Let's say, for example, that angle is I don't know, 220 degrees. Okay, because again, it's between 180 and 270, right? So I'm just estimating. Let's say it's 220. Can you draw a right triangle with a 220 degree angle in it? Probably not, right? Okay, so what we do is we say, all right, here's the terminal side. We always use the quickest path back to the x-axis, and we could draw our right triangle right there. There's a right angle. This little angle right here up in the corner would be our reference angle, okay, right there. How would we find its measure? Well, 220 was some amount past 180, right? So in this case, how far past 180 did we have to go to get to 220? In this case, theta prime would be 40 degrees. So the rule, if you're in quadrant 2, the reference angle is always the actual angle minus 180. I want to know how far past 180 did I go. Okay, and that's what we would use in reference. Instead of doing, you can't draw a right triangle with 220 degrees in it, but you can with 40. Okay, and we can use that reference triangle to answer questions about the 220. That's the point. Okay, all right, and one more option, fourth quadrant. Let's say we have this big old angle of 315 degrees, let's just say. Okay, and down the road they're going to say, all right, what's the cosine of 315? Need an exact value. Can't throw it in a calculator. Okay, you're going to say, all right, I can't draw a triangle with that in there. Okay, but what I can do is I can use the terminal side. Okay, getting back to the x-axis right here. Okay, there's an angle formed right up there in the corner. There is a reference angle. Here's my right angle. I can use this reference triangle. What would the measure of that angle be? How far short of going around the full circle are we? So the full circle is 360, right? We only went 315. We were 45 degrees short. That would be the measure of this angle right here. So the rule for quadrant 4 is always 360 minus whatever the angle is. Okay, 360 minus 315 in this case. Okay, so the deal is you're always trying to get back to the x-axis. So quadrant 1's the easy one because you don't have to worry about it. But quadrants 2 and 3, you're seeing how far away is the angle from 180. Okay, 150 was 30 away, 220 was 40 away. Okay, those are the reference angles. But in quadrant 4, you're going back to 360. So if your angle is 315, how far are you from 360? You were 45 degrees away. Okay. The key here, I guess, is this diagram right here. This shows in each of the 4 quadrants the options. Okay, and again, the idea is in quadrant 1, the reference angle just actually equals the angle itself. You don't have to do anything. In quadrant 2, you just need to see how far was your angle from 180. Same thing in quadrant 3, how far are you from 180? And then quadrant 4 is the one you're going, how far away were you from 360? Okay, so hopefully that helps. We'll be using it quite a bit, so it will sink in. But let's just practice a little bit with the finding reference angles at this point. Okay, so let's do a couple examples. Let's find the reference angle for each of these given. Okay, so let's say they give us an angle of 325 degrees. And again, they might say we might eventually need the cosine of 325 or something. And we can't draw a right triangle with that big of an angle, right? So we're going to figure out what could we use in reference to it, in place of it, that we could draw a right triangle with. All right, so let's think about this, okay? Let's just put the 325 down here, give ourselves some room. All right, so 325. So what quadrant does that end up in, right? So we know, again, 0, 90, 180, 270, and then 0 gets back to 360, right? Okay, so 325 is definitely in quadrant 4, right? So we start there. Going around that way, that angle, that big angle is 325 degrees, right? Okay, so the reference angle here, what we're going to use, again, always use the terminal side, just right there. And since we're in quadrant 4, getting back to the x-axis would be right back here. And it's always the acute angle. So right here, that little piece is what we're going to use as our reference angle. Okay, and our reference triangle will be here. Boom, boom. There's the right angle, reference angle right there. How many degrees is that angle? Okay, it's again, how far short of 360 were we? Okay, theta prime is going to be 360 minus the 325. Okay, our reference angle is 35 degrees. Okay, we could use 35 degrees to solve problems about 325 degrees. Okay, that's kind of the concept here. Okay, let's do a couple more. Let's do part B. At this point, let's just take, if it's in radians, let's just convert it to degrees, just to get it more comfortable at this point. So to take the 4 pi over 9, I know it's radians because it has a pi. Let's just replace, or let's multiply by the conversion factor of 180 over pi. Okay, and really what this is going to do, we're just going to be putting in the 180 where the pi was. It's 4 times 180 over 9, right? So see, it's really just like doing 4 times 180 because pi is 180. Okay, that's kind of the shortcut on doing those, which was mentioned in the previous video. But 4 times 180 over 9, that's giving me 80 degrees. Okay, so an 80 degree angle. Let's draw ourselves a little picture. Think about this. All right, 80 degrees. 80 degrees. What quadrant is 80 degrees in? I know we start here because every angle starts there. 80 degrees, so we're less than 90, right? So we are about there. Okay. Now, if we could we draw a right triangle using that angle? Yeah, right? Since it's less than 90 degrees, we can just use itself right there. Okay, so in quadrant 1, the angle itself, okay, and we should probably keep it in radians, but in quadrant 1, the reference angle is just the angle itself. Okay, so you don't even have to worry about it. You don't have to do any really calculation. As soon as I knew that that angle was 80, was less than 90 degrees, I knew we're in quadrant 1. I would know that the reference angle is itself. Okay, let's just do one more. Let's do part C. C is a big angle, 515 degrees. Oops, don't want that random mark there. So 515 degrees, right? Okay, so let's see what we got. Okay, one piece of advice. If the angle is bigger than 360, let's just subtract off one full circle. Let's get a coterminal angle from that and just give ourselves something easier to visualize where that is. Okay, because I don't care about doing the full circle. I just need to know where the terminal side is, right? So 155 is definitely in the second quadrant between 90 and 180. Okay, let's say it's around there somewhere. Okay, so I can mark that as 155. Okay, here's one of the uses of coterminal, right? I don't need to draw the full circle and then 155 more. I just need to know where it ends up. Okay, so my reference angle, when you're in quadrant 2 again, there's the terminal side. Quadrants 2 and 3, we're always getting back to the 180, to the x-axis that way. So right here's my reference angle. Okay, how far away from 180 are we? 180 minus the 155 gives me a reference angle of 25 degrees. Okay, that would be the angle right there, 25 degrees. We could do that as our right triangle. Oops, I don't know what's going on with my app here, but that's what we're gonna do. Okay, and we're gonna be using this quite a bit. So just kind of, practice the process a little bit. I know this is kind of weird, and it's like, what's the point? I don't want to do too much in this video though, so just kind of get used to the concept, I guess, and go back.